All right, it looks like it's time for us to get started. Thank you all for coming. It's my pleasure to introduce Samuel Graff from John Jay College, presenting using a model to give a grand tour of a first course in differential equations.
Good afternoon, everybody. Thank you all for joining us. And thanks to Ryan Winkle for arranging this wonderful session. My talk is about a shift in pedagogy on the first day of the standard course in differential equations. As we've heard in a number of the talks, students go through the calculus courses engaged in computations, and often they're trying to really find out what is all these techniques really good for? What purpose does it serve? And ordinarily, they get to the first course in differential equations, and the first day is full of a plethora of definitions about different types of differential equations and so on and so forth. And uh, I felt by that time the students are pretty much jaded. And 2 years ago, I decided to make a change. I took the traditional first day presentation of the course and I set it aside completely. And I decided, yes, I hear the chuckles. I set it aside completely, and I decided to, in some way, give a grand tour of the course that was very minimal on computations, but trying to emphasize the power of differential equations, what it could do, and in a way to fulfill what I've often said in my calculus classes, that the differential equations course is where the rubber really meets the road. It's where you look at real world problems, you analyze them, you try to get workable solutions, and learn to go forward from the information you get from these models. So having said that, uh, I put aside the first day's curriculum and put together what I thought was a reasonable presentation. And I decided to wing it a little bit by the seat of my pants. And let me kind of explain to you just what I did. And at the end, uh, tell you how it worked out. So the population growth problem is one that presents a lot of opportunities to introduce many techniques in differential equations. And you start with the simple Malthusian law. And of course, we all know that says the change of a population is proportional to the instantaneous population present. Uh, there are no surprises here. And what it does do, though, because the differential equation is simple enough, it provides an opportunity to speak about a few things very informally. Number one, it's kind of obvious that the derivative of the population is equal to a multiple of the population. And most students, if you ask them, is there any function you know of that upon differentiation replicates itself up to a constant multiple? And they'll tell you right away it's the exponential function. So you can multiply through by the factor of e to the minus RT, and the class usually readily observes that you have a perfect derivative on the left-hand side, and you either get a representation of the general solution or the initial value problem. Now, nothing here is very revealing. However, you then ask the class, well, is this reasonable? And it doesn't take long for them to say, well, a population can't grow forever because there are limitations in any ecosphere, limitations in room, resources, and so on and so forth. So we say, okay, well, let's try to modify the model a little bit to see if we can get it to be more realistic. So I suggest that we introduce a factor to the right-hand side, which is positive when the population is small, but at some sustainability threshold becomes negative. And so we put a factor of C minus dp on the right side, which will be positive when p is very small, but once the population exceeds the ratio of C over D, the factor C minus dp becomes negative, and at that point, your population will begin to decrease. So, okay, they're kind of satisfied with that, but you can make the model a little more complicated, because if you think of the very large predators, and most students are familiar with this, even though I teach in the heart of Midtown Manhattan, take grizzly bears, rhinoceros, tigers, and so on and so forth. The males especially are solitary. And if the population is too small, it'll die off. And so there has to be some type of viability threshold that has to be sustained in order for the population to grow. And so we add another factor to the right-hand side, similar to the first one. It's A minus BP, but you will forgive the slide. If you can see my pointer, there should be a negative sign in front of the entire factor. There should be parenthesis there and a negative sign. And what this factor will do is, when P is small, it's positive. And with a negative sign in front of it, it is therefore negative. So therefore, not until the population reaches some viability threshold does this factor become positive, because the term in the parentheses that you don't see there, aren't there, becomes negative. And then we get a resulting differential equation. Oh, let me go back, please. And you can see it's got three factors on the right-hand side. It's not very pretty, and we're not going to talk about integrating it. If I have a moment at the end of the presentation, I've got the solution at the very end of the PowerPoint deck. So what we do notice, though, at this point, is that one could attempt to anti-differentiate the equation because the variables separate. So in terms of this grand tour of the course, we've already built the model. We're mentioning the technique of separation of variables, but we're not going to apply it at all in this class, at this first class, to this model, because I can tell you, if you try to go through the computations, they're not pretty. And they certainly would not entice students back for the second class. But having explained the general concept of separation of variables, what you can do is go back to the Malthusian law, which was the very first simple equation, dp dt equals RT, and say, well, let's see if we can find a solution using power series, since after all, if you're at a loss for a solution, you might be able to use power series to find at least some numerical approximations. And this accomplishes two things. Students enter the differential equations course taking minimally at least 2 or 3 courses in calculus. That's either 8 to 12 credits. And the major unit at the end of calculus 2 is at least 4 or 5 weeks of infinite series. And throughout all that time, there are no applications whatsoever. Students learn about Taylor's formula, they learn about convergence, but what is it good for? So here we can help at least provide a partial answer. You can let the population be equal to a simple expansion in terms of time about the origin, and you can compute the derivative, you change the index so that all the powers of t have the same exponent, and you substitute, you get a recursion relation, and lo and behold, when you calculate the coefficients and put together the power series for the solution, most students will look at it and they'll say, oh my God, that's the power series for the exponential e to the RT. And a little further on in my presentation, we go back and use some of the techniques in power series, but the point I'm making is, ordinarily, this is the first realistic application of power series that they have seen. And it's a watershed for many of them. So going on, we go back to the differential equation, pardon me, for the population growth model. And we just go back to that. Forgive me for, there it is. If you take a look at it, it's quite obvious there are three equilibria. P is equal to 0, equal to V, the minimum viable population, and P equal to S, the maximum sustainable population. And I now introduce the notion of equilibria being stable or unstable by looking at this problem in detail. And I also mentioned that you can further plot these solutions since the equation happens to be autonomous, but I don't mention that word, on the PT plane, in the PT plane, if you use the second derivative to also determine the concavity of the solutions. However, the most important thing to do is to shift the discussion towards the geometric theory of differential equations and move it away from anything computational. And so instead of looking at the more complicated population growth model, I say, let's consider a very simple equation, dp dt equals p times p minus 1, where there are two obvious equilibria, p equals 0 and p equals 1. It was a little too much. Sorry there. Okay. And I say, well, look, the Malthusian model was so simple. Let's see if we can determine the local behavior about the equilibria, in this case, p equals 0 and p equals 1, just by looking at the linearized differential equation. In other words, treating the right-hand side as a finite power series and only taking the linear term. Well, the linear part, when p is equal to 0, is just the linear part of the right-hand side that you have in the differential equation itself. The right-hand side, there is p squared minus p. So the linear part is just minus p, and you have dt equals minus p. And the phase line is shown at the right. When the population is, p is positive, P is there, the right-hand side is negative, so the derivative is negative and the population is decreasing. Now, of course, we can't speak of a negative population, but we're talking about a differential equation at the same time. If P could be negative, then the right-hand side is positive, and what you see is distinct, that all solutions tend towards the equilibrium P equals 0. Now, the linearization of the differential equation near P equals 1 requires a change of variable where you introduce U equals P minus 1. However, I frequently don't do it this way. What I do is I take the right-hand side and use Taylor's formula to expand the right-hand side about P equals 1. And the reason I do that is they've never seen an application of Taylor's formula before in a real context, in a problem that has meaning. So in any case, excuse me, the linearization turns out to be du dt equals u. And what you have now, and by the way, this moved the equilibrium from P equals 1 to the origin at U equals 0. So what you have when U is positive or the population P is greater than 1, you have solutions increasing. On the other hand, when U is negative or P is less than 1, solutions decrease. So it turns out that the equilibrium P equals 1 is a source, and solutions leave the source, both whether P is greater than 1 or less than 1. Now, if you put it all together and you get the phase line, you have a reasonable picture of what happens. And also, if you consider the phase line as the family of initial values, you have quite a decent global representation of what is happening. Solutions whose initial values are below the sink don't really have any meaning in terms of a population problem. But if we look at those above the sink, we see that if the initial population is less than 1, it's not viable. It's going to die out. On the other hand, if the population is greater than 1, it will increase. Of course, again, this is not the full population growth model. I'll make a few comments about that at the very end. So let me move on. The last topic I tried to cover is a brief introduction to bifurcation. And I use the same simple differential equation, dp dt equals p times p minus mu instead of 1, where mu is a parameter. And there are 3 cases that are considered. Mu is either greater than 0, equal to 0, or less than 0. Now, when mu is greater than 0, you get the same behavior on the phase line that you do when mu is equal to 1, that what I just discussed earlier. So I kind of move over that quickly. However, when mu is 0, we now get a degenerate situation because the right-hand side of the differential equation does not have a linear term. And the linearization is just dp dt equals 0. There is no non-trivial linear term. So all the solutions are constant solutions. On the other hand, now when mu is negative, there is an interesting phenomena that occurs. If we let mu equal to minus sigma so that the parameter is again positive, the differential equation is modified very slightly. The right side becomes p times p plus sigma. You have two critical points, P equals 0, P equals minus sigma, and you have the linearized differential equation as we've had earlier. And again, sigma being positive means that P equals 0 now is a source, because when P is positive, dP dt will be positive, and when P is negative, dP dt will be negative. Now, what is kind of interesting at the end here, if we put it all together and look at what happens when the parameter mu is varying, there are still two critical points always, P equals 0 and P equals mu. When mu is positive, the equilibrium P equals mu is the source and P equals 0 is the sink. But when mu becomes negative, although the source and the sink keep their relative positions, P equals 0 goes from being a sink to a source, and P equals mu goes from being a source to a sink. And the students find that somewhat amazing. Now, when this is all over, you might ask me, well, what do I expect? What is their reaction? Well, if there's time, I go back to the population growth model and I put the three equilibria on the phase line. And what we find then, if you allow me to go back to the population growth equation, what we find is that the equilibrium P equals V, that's the minimum viable population, is unstable. I think Brian is telling me that, Gavin rather is telling me, am I at my 2 minutes?
Almost there. You got 2.5 minutes right now.
Okay, I just looked at my watch. Thank you. We find that viable level of population is an unstable equilibrium. If you're below it, solutions decrease. If you're above it, solutions increase up to the sustainable population, P equals S, which is an equilibrium. And that equilibrium is stable. So if the population in the ecosphere is larger than the sustainable population, it will decrease. And if it's less, it increases to that value. And at this point, some of the students are on the edge of their seats and they're saying, wow. And why are they saying that? We did all of this without any computation. It was all analytical reasoning. Now, let me show you why you wouldn't want to get involved in computation. If you work out the solution using separation of variables and integration by partial fractions, let me skip to the end of the deck here if I can. Whoop. Don't look, close your eyes. Okay, if you look at the very last line on that last slide, that is the closed form solution. And it's an implicit solution. Inverting it is it takes a lot. It takes handstands and everything to do. And what I skipped over, these are all the calculations just to get there. So you didn't want to see them either. So I usually get what I call buy-in after the first day, about somewhere between 30 to 40% of the class. And what do I mean by buy-in? That I pique their interest enough that they want to come back and see more during the second class. So again, thank you everybody for coming. And if you have any questions, please feel free to ask. Thank you very much. Okay, if there are no other any questions, then I guess I would end the session. Ms. Brown, do you have any questions? You're the only other participant left. But if not, I'll end the session. So thank you.
Hi, thank
Yes.
you. I was only in for like the last 3 minutes of your talk. I'm sorry. Um, so
Okay.
yeah, I gathered that you're using this as a introduction, like a first day of class.
Yes, I threw out the traditional first day
Yeah,
litany of definitions and classifications of equations,
yeah.
and try to give them a whole tour of the course, a little bit of the phase line, a little bit of power series, linearization, and bifurcation.
That's really cool. So from your abstract, I gathered that you were starting with a simple exponential growth model, and then you must have been refining the model and making it more
Yes,
complex in order to bring in all of these, the tour of the
right.
course.
And of course, at the very end here, you saw there were like 3 or 4 slides at the end that have the solution to that equation. And if you did that the first day, every student would run to the registrar's office and drop the course.
Sure. Yeah.
And one of the things that came out at the joint math meetings, Brian Winkle had asked me to give this talk here again, is that we really need to introduce more modeling into the calculus sequence. And I'm teaching 2 sections of Calc 1. And as soon as my students have the ability to differentiate exponential functions, and maybe they get the first lesson of anti-differentiation before we go into the Riemann integral. These are now 4 credit courses at the college. I may stop and take, since the classes are 100 minutes, which is quite a long time, take half a class, 50 minutes, and do the Malthusian growth model.
Yes. Yeah, that's so cool. I agree. I teach a lot of calculus as well, usually Calc 1 and occasionally Calc 2. And I'm trying to incorporate more modeling in those courses as well. And I used this past fall, I used a semiode scenario in my Calc 1 class that Jenny Dambros had modified for Calc 1. So they were solving, it was the oil slick problem. So you have sort of incomplete data, but you can get basic let's see. So from the data, you can calculate some discrete derivatives, and then you do a linear regression to find a differential equation model that is linear. And then the students just solved it by guess and check. I showed them how to guess what might be a solution to the differential equation and check it by differentiation. And so with nothing more than chain rule understanding, they were able to, solve their first differential equation and use that to investigate the spread of this oil slick. And Jenny's done another one where she's looking at cancer growth, tumor cancer growth. And again, it's a semioid scenario that she adapted specifically for calc classes. And I think that's really cool. And I might use that one next year. But yeah, the calc students benefit a lot from seeing this at that level.
Well, this is the first time I'm at SemiODE, but when I was at JMM, Brian sponsored 3 sessions over a day and a half. And what keeps coming through in the discussion again and again and again is that we have to bring the modeling down into the calculus courses.
Cool. I'm all about that. Yeah.
And I'm hearing it here today, implicitly, but you're hearing it all along. And furthermore, it's not coming from the young Turks who are just out of graduate school with their PhDs. It's coming from all the people who are in the, shall we say, the second half of their careers.
Who have taught for many years in the more traditional curriculum for calculus and see the change that's needed.
Yeah, I don't think you need to change the traditional curriculum. You have to cover the same material, but let the orchestra play in the background.
Sure.
Strike up the band, let it be interesting. It doesn't have to be dull.
Yep. That's awesome.
So I don't know how many people attended. I saw at the end there were only 4. I couldn't get that up while
there were 9 when I came in, which was like
good.
At 23. I came in very late to your session and I apologize for that. But
okay, so there were 9 when you came in. So there may have been more a little earlier.
Oh yeah.
So
yep.
Yeah, so anyway, I'm glad you got something out of it, and hopefully some other instructors will literally set aside that traditional first day of the course and just do something so different.
Yep, absolutely.
And one other thing also is I realized my field is differential equations, is that instead of computation, it was Poincaré that developed the geometric theory. And we really don't do too much with it in the first differential equations course. And it's powerful. And if you go to higher dimensions, 3, 4, 5, that's where, those quote pure mathematicians would be surprised. You have to bring in algebraic topology and all sorts of things to actually analyze the problems, because the surfaces that are generated can sort of self-intersect. I mean, not quite, because you have uniqueness, but still, they're manifold opportunities. So we ought to pay more attention to that as well. I mean, there's so much beauty in the discipline, and I think I know where all the computational emphasis came from. My undergraduate years were at Rensselaer Polytechnic Institute. It's from the engineers.
Sure. They needed that computational background. And so then that became an important part of the math classes.
Yes, at least one thing we was spared from, that we had to take one elective in another department. So I took a year of circuit theory. They didn't do Laplace transforms in the differential equations course.
Okay.
It was confined to the circuit theory course.
Oh, interesting. Yeah. Okay. Was there a topic that replaced it in the differential equations class then that we're not covering now?
No, I mean, in other words, you have the Green's function, which essentially is a solution operator for the inhomogeneous linear equation. The Laplace transform is used to set up the same thing in what the
Yeah.
engineers call the transform domain.
Sure, sure.
And what you wind up doing in the differential equations course when you include Laplace transforms is just having an annoying exercise on separation of variables.
Yeah. Yep.
So, and nothing is gained. Whereas when you look at the Green's function, you're not in a transform space, you're in actual time domain,
Okay.
and you have an integral representation. So you have a kernel in a sense, and you can talk about how does a solution behave given a change in the inhomogeneous right-hand side of the equation. You can do analysis.
Yeah. Yep. Yep. That does sound far more interesting.
It's more interesting.
Yeah.
And one thing I learned as an undergrad, I mean, the engineers are like with blinders, so focused on the solution. You couldn't leave any answer in closed form, like I'm trying to think. You couldn't say, well, use Kramer's rule and it comes out, or leave it. No, you had to work it out, and you had to get an approximation to 2 or 3 decimals. But the little cohort of math majors, we got our revenge. When it came to the Laplace transform unit, the engineers were flummoxed and we ran away with it.
There you go. Aw.
So hopefully you can take this back with you and maybe get some of your colleagues to change that first day's presentation.
Awesome. Yeah. Thank you very much for presenting. I really appreciate it.
Okay, you're welcome. It's nice meeting you. And
too.
I'll end the session now and see what else is being offered. I mean, it's
Yep.
a great meeting.
Yeah. Yeah. I really love this expo. Yeah.
Yeah.
Thank you for presenting.
Okay, take care.
You too.
Bye-bye
Bye-bye.
now.